In this section we want to take a look at exponential functions to kind of get a handle on what they are. You see here a function, 5 raised to the x power. Notice that the base, the bottom number, is the 5, and the variable is up in the exponent. This is what exponential functions are. The variable is in the exponent. That creates a lot of issues with handling these sorts of functions. Let's take a look at the graph of 2 to the x, and we will do this by hand. You can draw graphs of these on your calculator, as I'll show you in class, but here's what we would do by hand. If we pick us a table of values and pick out a value for x and substitute it in, 2 with an exponent of 1, 2 raised to the 1 power, is 2. We'll draw us a graph. We'll put a dot at 1, 2. Pick out another number for x. Plug it in. 2 raised to the 2 power would be 4. Here's the dot 2, 4. 3. 2 raised to the 3 power is 8. Here's the dot 3, 8. If we pick out a number like 0, it gets a little trickier. 2 raised to the 0 power. You might remember this from when you first learned about exponents. Anything to the 0 power comes out to be a 1. So 0, 1 is the dot right here. And choosing negative numbers. Again, it's a little strange, but you need to get a handle on dealing with negative exponents. 2 raised to the negative 1 power is the same as 1 over 2 to the positive 1 power. The dot negative 1 and 1/2. If we choose a negative 2 for x, 2 raised to the negative 2 power is 1 over 2 to the positive 2 power, which is 1 over 4. Negative 3, the last dot we're going to put, 2 raised to the negative 3 power would be a 1 over 8. The dot at negative 3 and 1 over 8 is way down by the x-axis. Now, a little bit of conjectures here. If you keep using bigger numbers for x beyond the 3 that we ended up with, like 4, 5, 6, 7, and 8, you're going to keep getting bigger and bigger answers. So the dots are going to go higher and higher. If you keep using numbers beyond the negative 3 that we stopped with, negative 4, negative 5, negative 6, you will always get positive answers, and they will continue to get smaller and smaller and smaller. And so the graph would look like this. To the left, the graph never actually touches the x-axis. The x-axis is called the asymptote for the graph, and it goes forever to the right. This is a typical exponential function. Crosses the y-axis at 1, up to the right, down to the left, never touches the x-axis. The domain of all exponential functions from here to forever would be negative infinity to infinity. The range, however, what we just got through saying is it never touches the x-axis. Y will never be equal to 0. So the range is from 0 to infinity, not counting the 0. You never have an answer of 0. Let me show you some of the contrast of the different bases. This is the one we just did, 2 to the x. Here's the graph of 3 to the x. Here's the graph of 4 to the x. Notice I've got these color-coded for you. Graph of 1.5 to the x. And then the graph of 1.2 to the x. And notice some of the similarities. Every one of them cross the y-axis at 1. Every one of them rise to the right. They just rise at different rates, depending upon the size of the base. Every one of them fall off to the left, but never touch the x-axis. And so they're all pretty much the same sort of graph, just different shapes. here are two graphs, 2 to the x and 3 to the x. What I want to show you is a special number that occurs a lot in math, science, business, and that number is this. Now, it shouldn't be a big mystery that the graph of this is going to be in between the red and the blue. And so this is the graph of something called e to the x. The e that's used here is referred to as the natural base. The natural base is the number 2.71828, etc., or approximately 2.72. You don't need to commit that to memory because it's in your calculator and you can get it whenever you need it. The point is remembering that this lowercase letter e is a number. It is not a variable. And so this is a typical exponential function. This is called the natural exponential function because e is the natural base. Let me show you some of the things that we studied in the earlier section, the transformations. Here's the graph of 2 to the x. And up here in the top, if we replace the x with x minus 3, do you remember that shifts the graph to the right 3 units? I've highlighted the point here, 0, 1, on the 2 to the x graph, and that point is shifted to the right, and the whole graph is shifted right. This graph, if you look at where the minus 3 occurs, is shifted down 3. Now notice the asymptote would be at negative 3. 2 to the negative x. Remember, the negative multiplied flips the graph. If it's on the x, it flips it sideways. Now these are actually things that you could type into your calculator and not know the transformations. It's just a matter of understanding the graphs. And 3x, remember, stretches the graph, shrinks the graph, and this does all of it. 2 to the x minus 5, the negative on the front flips it upside down. The minus 5 on the x shifts it to the right 5. The minus 4 at the end shifts it down 4. This graph flipped over, shifted to the right, shifted down, and again, because of the size of the numbers here, if you were to type this into your calculator and draw the graph, everything would be fine. The issue occurs when we start using larger or smaller numbers. Look at this one. Do you know what the graph of this one would look like? Well, we're not actually going to go through the graph, but I can make a guess that the E graph is going to cross normally the y-axis at 1, curve up to the right, down to the left. I know the 1500 on the front is going to expand it. So instead of crossing at 1, it's going to cross at 1500. If I'm drawing the graph on my calculator, I need to set my scale so that I can see 1500 on the y-axis. However, that's not the intent of this particular thing. What if we were to ask to evaluate f parentheses 10? Now, we kind of showed you that whenever we were drawing the graph in the very beginning. Plugging a 10 in place of the x is what we need to do. Now, if we take out our calculator, we can do this by typing the 1500 using the EX key on the calculator and 0.04 times 10. And so these are not things that you're expected to be able to do by hand. Natural exponentials. F of 20, plug it into the calculator. F of 500, plug it into the calculator. Now these are things you need to at least pause the video and try it on your calculator and make sure you know how to type these. Let me just point out on this last one, do you notice the little e here? This is a humongous number. The scientific notation, the E11, means actually you got a 7 and then 11 numbers past it. Now, I don't know what that's going to be, millions, billions, trillions, but that is not a 7.2 as the answer. It's 7 and then 2, 7, 7, 4, 7, 7, 9, 3, 1, and then more zeros. Enough zeros to make 11 numbers past the 7.